In the next series of videos, I want to start introducing how to prove mathematical statements, how to show that they're always true. And the most important, in some sense, are implications, are conditional statements. So, if P, then Q. Now, before we start, I do want to kind of tell you something about the relationship between conditional statements and universally quantified statements. And in some sense, in mathematics, conditional statements like this usually have a quantifier built in some sense. So a lot of times when people write down a conditional statement that's true, they assume that you're talking about for all x in some sort of set, some domain. And usually it's quite clear. If it's not clear, then it's usually specified. But given the same domains, what's really cool is that a conditional statement and a universally quantified statement are the same thing. Let me give you an example. Imagine the following. So if I had the following conditional statement, if C is a cat, then C is a mammal. And the way we can reword that, and I'll explain this in a second, is all cats are mammals. And for conditional statements that are always true, you can do this. I want to draw a little bit of a diagram to show why this is the case. Let's do all cats are mammals first. So I'm going to put a fence here, a circular fence. Imagine I'm looking up on the earth and I'm collecting all the cats and I'm putting them inside this fence. So there's all my cats. So imagine if I wanted to collect all of the mammals in the world and put them in a fence, knowing that all cats are mammals, how would I draw that fence? Maybe pause the video now and try that yourself. Well, now that you're back, if you think about it, all cats are mammals. So if I put all of the mammals in a fence, those cats have to be in the same fence. So the cat's fence is included in the mammal's fence. So here are my mammals, here are my cats. And for a true conditional sentence, this makes sense. If C is a cat, then C is a mammal. So if C, we just use the variable C, let's say C lives here, it's inside the cat fence. Well, it's also inside the mammal fence. So if C is a cat, then C is a mammal can be reworded as all cats are mammal. And all cats are mammals, sorry. And this holds for all conditional statements that are true. And that's going to be kind of the idea that we're going to use to prove these conditional statements. Now, let's relate this idea here to the truth table for a conditional statement. Let me remind you what that is. Let's draw it out. So we have P, we have Q, and we have if P, then Q. And remember that a conditional is false exactly when the if part is true and the then part is false and true otherwise. And if you remember, this here is, we call this the dreaded row. And we like conditional statements where that does not happen. Then they're always true conditional statements. Remember, there's that baked-in universal quantifier. So the whole idea is showing that that never happens. And you can kind of see where the other three rows are in that little diagram that I drew above. Let me label the rows in green here. So we'll call this row 1, row 2, row 3, and row 4. So row 1 is when P is true and Q is true. So in the diagram, it's when something is a cat and is a mammal. So the place in the diagram where row 1 exists is here. Something that is a cat and is a mammal lives here. Row 3 is P is false and Q is true. So that's saying it's not a cat, but it is a mammal. So where in the diagram do we have things that aren't cats but are mammals? In fact, it's here. So things like dogs or raccoons or whatever live in this area. That's when the if part is false, or the all is false, but the next part is true. The then part is true. And then finally, oh, I made a mistake here, guys. Sorry. Let's fix this. This should be, of course, a false. I wrote a true there by mistake. This should be a false. So the last area is something that isn't a cat, so P is false, and Q is false, so isn't a mammal. So things that aren't cats and aren't mammals are outside both fences. And that is here. And you can see that's every area of this diagram. Inside both fences, between the inner and the outer fence, and outside both fences. There's no place for row 2. There's no situation in an all situation where the if part is true and the then part is false. So the whole idea is showing that this dreaded row never happens. And we're going to learn 3 different techniques to show that. And we're going to scroll down and talk about them now. All right. I'm going to leave this truth table up because it's going to be important to explaining what's happening here. So the first way, and this is kind of the most common way, it's called the direct proof. And it's basically saying that you assume the if part is true, and you show that the then part, Q, must be true. That's the key. And the reason that that works is as follows. Well, if you're assuming that P is true, that means that you're either in row 1 or row 2. And remember, we want to avoid row 2. So the whole idea will be showing that it's impossible to be in row 2. That if you can possibly be in row 1 or row 2, you must be in row 1, which means that Q must be true. So that's how a direct proof works, and we'll get lots of practice with this in the next coming videos. If you think about it, well, there's another way of doing this as well. Instead of assuming that P is true, you can assume that Q is false. And I'll do this one maybe in yellow. If you assume Q is false, well, what possible rows could you be in? Well, Q is false in rows 4 and 2. And again, we want to avoid row 2. So that means we need to show that the dreaded row never happens, that P is never true. So P must be false. And that's a proof by contraposition. And also you can think about it, if you like, as proving the contrapositive statement, if not Q, then not P. Since if we're assuming Q is false, it's like assuming this if part is true. And showing that P must be false is the same as assuming this then part is true. So you could think of it, a proof by contradiction, as well as a direct proof of the contrapositive. Both ways mean the exact same thing. There are two methods. And our third method is something called a proof by contradiction. And basically, for if-then statements, it works as follows. We assume that we're in this dreaded row, that there's a counterexample, that this if-then statement has something that makes it false, where the if part is true and the then part is false. So we assume that, and we show, basically, that if that happens, mathematics blows up. We end up with some contradiction. And these three methods we're going to learn in the coming videos. The next video we're going to learn, is going to be a little short one, is going to be how to write even and odd numbers algebraically. They're really nice, simple objects to be able to use to prove relatively easy statements. That'll be good practice for us for learning the methods of proof. So expect in the next video just a nice quick one on learning how to write even and odd numbers in general algebraically.